So the last topic in engineering physics is about resonance and damping. It's kind of like an application of simple harmonic motion. And basically, like there's only one really new equation to know, and all this stuff is based off of simple harmonic motion or energy. So here's kind of an application. Like here's an example of what it means when something's damping. So if I take this mass on a spring, see it okay, and I were to pull it down, you can see how it should go forever, but eventually, because of dissipated energy, it stops. It slows down. In fact, every single time it swings, it dissipates energy, and it loses some energy to the environment, and it stops. So there's an efficiency factor, because of this laws of thermodynamics again. But let's say I applied a force at the right times, I can actually keep it going. If I apply a force at the correct moments, I can actually keep that that thing oscillating for as long as I keep applying a force. So damping is basically a fancy word for dissipated energy in a spring system. So like shock absorbers are a great example of where this is very useful. Like if you drive along in your car, you don't want to hit a bump and go boom, boom, boom on every single bump. You want the shock absorbers, or on your bicycle, to absorb that shock so it dissipates the energy so you don't feel it as much. Maybe it looks little small bumps along the way versus boom, 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 jarring. So shock absorbers are a good example of where damping or dissipated energy is a good thing in the spring system. A lot of times in buildings, like for skyscrapers, they put in damping mechanisms so if there's an earthquake or something, it doesn't feel that. It kind of dampens it so it doesn't feel as much vibration to save the building from being completely destroyed. On the contrary, sometimes you don't want damping. You want things to last a long time. So if you're on a swing set, if you were just swinging, eventually you would just die out and stop. So with the swing set, you have to pump your legs and your arms, or at least your legs, at the right moment to keep that damping from taking over. So you're kind of, with the same frequency as the swing set's moving, you have to push with your momentum to keep that swing set going at the right time. So let's look at an example. Let's say I have a 1 kilogram mass on a spring and it's oscillating up and down. So maybe I can bring this back. I got this 1 kilogram mass on a spring, and first thing I do is I give it some elastic energy. Then I let it go up, down, and notice it dies out. So what's the graph look like? This graph, it's displacement versus time, it's velocity versus time, it's kinetic energy versus time, and elastic energy versus time. And see what can we do with this, and then talk about our equations and what they mean. So let's start with displacement versus time. I'm going to go with a different color here. So I'm going to say I started on the top. I raised up the mass and raised it up at the top. It had some displacement. Then, after some time, it reached equilibrium. Then it went below equilibrium. Then it went back up to equilibrium. And then it went past equilibrium. So it completed one cycle there. But this isn't exactly true. If you notice this, I'm going to continue the graph. There's something I should really think about, especially with that system I just saw, about this graph. Does it actually reach the same height and same displacement every single time? Probably not. It's probably going to get a little bit lower each time until it just reaches equilibrium. And eventually it just flattens out. That's what the graph looks like over time. So after one cycle, it's hardly noticeable, but after a couple cycles, it starts to flatten out. Velocity graph looks very similar. It starts off with zero velocity, it wasn't moving. Then it moved, it actually moved down, because I lifted it up, so it moved down, negative velocity. Then it would go back up to 0, and then as it's moving up, as a positive velocity, but it's moving a little slower. And this graph is going to do the same thing, except it gets slower and slower and slower. The kinetic energy graph, it starts with no kinetic energy, then it has a lot of kinetic energy because it's moving, then it has no kinetic energy, then it has a little bit less kinetic energy, and it does the same thing. Over time, the hills get smaller and smaller and smaller. Elastic energy is exactly the opposite. It starts with elastic energy. It goes down, up, and then every hill gets a little smaller and smaller and smaller because of dissipated energy involved. So let's just get some numbers here. So let's say that's a 1 kilogram mass, and it reached a velocity, a maximum velocity here of 5 meters per second. I guess it's -5, but I'll put -5 meters per second. And then after another cycle, it goes to -2.5 meters per second. It lost some energy. Well, let's try to answer some questions. Question 1 is, let's calculate its starting energy. How much energy did it start with? Well, to do that, we're going to assume that that's what it started with. That initial kinetic energy is what it started with right there. So we have 1/2 mv squared. Its starting energy is 1/2 times 1 times -5 squared, which is just 2.5 joules. Okay. How much energy did it have after one cycle? So this is the first cycle. After one cycle, it lost some energy because its energy is 1/2 mv squared, but it's 1/2 times 1 times 2.5 squared. So I do that, I get, wait, I screwed up. 0.5 times 5 squared. Sorry, this is 12.5 joules. My bad. It's 12.5 joules. No, this one is 0.5 times 1 times 2.5 squared. So it's 3.125 joules. So look at that. Question 1 was how much energy did it start with? Question 2 was how much energy did it have after one cycle? So here's some things we can calculate. What is the efficiency of this spring at damping? Well, what's the efficiency of this spring? Well, efficiency is just the useful, boom, over the total. You always take the smaller number over the bigger number. So it'd be 3.125 over 12.5. And so the efficiency is 25%. So 25% of the energy went back into the spring, 75% got dissipated, it damped out. So the spring is very efficient at damping, not efficient at keeping it going. The last thing we can talk about is something called Q factor. That's the only new equation in this unit, is Q factor. The engineers use this to kind of determine how good something is at damping. Kind of like the opposite of efficiency. Efficiency measures how good is something that could keep. The higher the efficiency, the longer it's going to last. Opposite of that is Q factor. The higher the Q factor, the better damper it is. The better it is at damping. So it's going to last shorter. So Q factor is just a number. The higher the number, the better it is at damping. And here's the equation for it. It's kind of a weird equation, but it's literally just plug it in. So Q, damping, Q factor, is equal to 2 pi times energy stored. Another way to think of that is how much energy you started with over how much energy you lost in a cycle. So using those exact same numbers, if I want to calculate my Q factor for this example, I would say Q equals 2 pi times energy stored. That's my starting energy, which is 12.5 over 3.125. So 12.5 over 3.125 is 4. 4 times 2 is 8. So it's 8 pi, whatever that is. 8 times pi. So my Q factor is 25. Ish. It's just a number. The bigger Q is, the better it is at damping. So, yeah. Now typically you want shock absorbers to be like in the thousands. You want it to absorb a lot of the energy, so its Q factor is going to be in the thousands. So there you have it. Now, one thing that we could ask, we did it with kinetic energy. We could have done the same thing with elastic energy, but instead of me giving you the mass, I would have had to give you the elastic constant of the spring, and then you'd use the x graph instead of the v graph. So depending on what you have velocity of mass, then use kinetic energy. If you have a displacement and elastic constant, then use elastic energy. So there you have it.